Hello friends, welcome to this video. And in this video, we are going to implement the MultiResUNET architecture in TensorFlow. And we are going to see how it is different from the UNET architecture. So let's take a look at the block diagram. So if you see the block diagram of the MultiResUNET, you can see it's an encoder-decoder architecture consisting of multi-res block and the res path. These are the two novelties which are introduced in this MultiResUNET. So this network is basically a modification and improvement upon the UNET architecture. So let's see what are the modifications which are made in the UNET. So first of all, the normal convolution block which is used in the UNET is now changed to multi-res block. And second is that the simple skip connection are now called the res path. They are now changed to res path. Some additional things are introduced to improve the features and improve their performance. So here's the two diagrams. In the left we can see the normal convolution block which is used by the UNET, and in the right side we have the multi-res block which is used by the MultiResUNET. So if you see the convolution block, it's really simple, and if you see the multi-res block, it's really a layer heavy. It contain number of parameter more than the, I believe, the convolution block. So if you see the multi-res block, it contain two essential features. If you can see, it contain heavy concatenation of 3 convolution layer, which is the feature of dense net. And second, it also contain an identity mapping or shortcut connection from input connecting the rest of the feature. So it contains features from both the network, that is dense net, and second is the res net. So now let's try to implement this multi-res block in the TensorFlow, and let's open our text editor. So first of all, we are going to implement the simple convolution block. This convolution block is not for the UNET one. Is basically we're going to take some input and we're going to follow the convolution layer and batch normalization layer. Okay, so first of all, we're going to take the x as the input, which is a previous feature map. Okay, then we're going to take number of filters here. Next is the kernel size. After that, we're going to say padding equals to same. We are going to provide some default values to them. Next, we're going to say act, that is activation function. By default, we're going to say it's to true. So now we've used a convolution layer. We're going to say x is equals to con 2d. Okay, now we use a convolution layer, and next we're going to use a batch normalization layer. Okay, so these two layers are really used. Okay, these two layers are followed. After that, we're going to have an optional layer. So these two are compulsory layer, and then we have an optional layer. If activation is equals to true, then we're going to say x is equals to activation, and here we're going to say relu. So we're going to use relu as the activation function here, and we're going to return x. So this is a normal convolution block we have built so that we don't have to repeat layers, that is convolution layer, batch normalization, relu layer every time, so that we can simply just call this function, give it some argument, and we get the output. Okay, so this make us more productive. Okay, now we are going to implement the multi-res block. If you see, first of all, we have 3 convolution layer. Okay, and each is followed by batch normalization and relu. So let's do that. Let's define the multi-res block. First, we take x. Second, we take num filter, and third, we're going to say alpha. It's a value which is used by the multi-res block. I'll explain you what it is. So we're going to say w equals to number of filters multiplied by alpha. Okay, if you see, we have 3 convolution layer. So let's do that. So first of all, let's say x0 is equals to x, because we also have an identity mapping. If you see, so we need to preserve our original input in some variable. So we're going to say x0. Then we're going to say x1. So 3 convolution block. Okay, so we're going to call them x1, x2, and x3. So x1 takes uses this convolution block function. It takes the x0 as input, and then take number of filters. So if you see, we have used w and multiply with some constant value. So what are we doing here? We are not directly using the number of filters. We are gradually increasing the number of filters here. So that's what we do in these 3 continuous convolution layer. We gradually increase the layer so that number of parameter does not increase at once. they gradually increase, and 3 refers to as the number, the kernel size, that is 3 by 3. Next, if you see the block diagram, we have a concatenation. So that's what are we going to do here. So let's concatenate these, the output of these 3 convolution layer. So we're going to call it xc, that is x and c refers to convolution. So that's my way of writing the name of the variable. Let's again go back to this block diagram. So after that we have batch normalization and an addition of the identity mapping. Okay, let's do that. So let's now we're going to add the batch normalization. So next we need a 1 by 1 convolution. So let's say SC, that is shortcut connection. So this SC does not refer concatenation, refers shortcut connection. Okay, let's call it conv block. Okay, now what do we need? That is input, original input, x0. Now we need number of filter. Let's call f nf, call them nf. Okay, then we're going to say 1 and act equals to false. Okay, now this is good. Now we need number of filters for them. So if we see, as we are going to add, let's go back to the block diagram first. You see, we are going to add the identity mapping with the batch normalization, which is a concatenation of 3 features. So a number of features, okay, number of filters would also be an addition of 3 features which are used in these layers. Okay, now we are going to do some ReLU layer. We're going to add some ReLU and batch normalization layer. Okay, we have add these 2 features, that is xc and sc. Okay, and then it is followed by ReLU, batch normalization, and we have written the required output feature. Okay, now we are done with the multi-res block. Now we'll move to the res path. So in res path, we take the feature from the encoder, that is a skip connection, and it passes through this res block. Okay, not this res path, we can call it, and this output is then concatenated with the features in the decoder block. Okay, the reason behind introducing this res path, that is a block between in the skip connection, is that the author of the MultiResUNET paper says that there is a semantic difference between the feature of the encoder and the decoder. So they cannot be directly concatenated, what we do in UNET. So they use some layers in between, while in between, and these features, that is feature of the encoder, are passed through these layers, that what we call as res path, and then the output is concatenated to the decoder. Okay, so now we are going to build the res path here. Okay, let's now go back to our code. So we're gonna write a function called res path. Okay, it's going to take the input, that is the previous feature map or feature map for the encoder, number of filters, and the length, that is how many times it is repeated, because these are repeated. So we're going to say for I in range length. So these are going to repeated length time. Okay, so we're going to say x0 is equals to x. Okay, let's now we're going to have 2 convolution layers. So first is a 3 by 3 convolution layer. We're going to call it x1. So take x0 as input, the number of filter, and 3 as the kernel layer. Then it is followed by a shortcut connection. Okay, we're going to call it sc again. Then it is going to be followed by addition, an activation layer, and a batch normalization. Okay, and finally we are going to return the x, that is the output of this res path. Okay, so these are the 2 blocks which we have built for now, and these 2 blocks are going to be used to build both the encoder and the decoder layer. Okay, now let's start building the encoder block. So encoder block takes x, that is the input, the number of filters, and then the length of how many times you're going to repeat the res path. If you see the block diagram of res path, you can see we have provided n value. So this is repeated n times. Okay, so first of all, it is in the encoder block we have a multi-res block. Okay, fine. Then we have a shortcut connection. Okay, that is not shortcut connection, skip connection. So this, the output of this x is now passed through this res path and then concatenated to the decoder. So we're going to take the res path, okay, We're going to provide the required number parameter. It is going to be repeated n times. Next, it is followed by 2 by 2 max pooling. And we're going to take the input as x. Okay. So this x, not x, that is s, is the skip connection, and x refers to as output for the next layer. Okay. We can also call it p. So we can say return s and p. So s is the output of res path, okay, whose input is the output of multi-res block, and the input for the multi-res block is the input for the encoder block. And p is basically pooling operation, where we reduce the number feature by half to reduce the computational cost. So we're going to say build multi-res unit, and it's going to have one parameter, that is shape. Okay. So next we are going to define an input layer. Okay. So now here begins our encoder block or encoder network. So we're going to say P0 as inputs, just for convention. So first of all, we're going to call our encoder block. Okay. We're going to say input as P0, number of input filter is 32, and this res path is going to be repeated 4 times. Okay. That's why we say 4 here. And it's going to output 2 things. First is a skip connection and the output of the pooling layer. So what we're going to do, we're going to copy this thing from here, and we're going to again paste it. So this time it's second encoder block. We say S2 and P2 just for convention. Then input for the second encoder block would be the output of first pooling layer. The number of filter here we increases to 64, and we reduce the length to third. Same we're going to do again. We're going to say S third and P third, followed by encoder block. We say P2 as the input for the encoder block. Number of filter again doubles to 128, and we reduce the repetition of res path to 2. And the final encoder block, S4 and P4, we're going to say encoder block input would be P third, then number of filters 256, and it is repeated 1 time. Okay. So encoder is done. Now comes the bridge. So bridge is a simple multi-res block. Okay. And we take, and in this in the bridge, the input acts as the output of the output of the encoder block. Okay. So the output of this entire encoder block is this P4. So we're going to take this P4 and number of filters as 512. Now comes the decoder block. So let's do this. So now let's try to run this block till now and see what is happening. Okay, see if it is working or not, we are getting the required thing or not. So let's say for now our shape is 256 by 256 by 3. 3 basically refers to the RGB channels. Generally we take RGB image. We're going to say build ResUNET because until now it does not return anything. Okay, so we're going to go to a terminal. Okay, let's see. So you can see it works successfully because we don't have any error. But to see anything, what we're going to do, we're going to print the shape of B1 for now, just to get an idea if it is working or not. Okay, so you can see we have the required shape, that is 16 by 16 by 8 5/3. Okay, so you can see it is working for now. So now we're going to build our decoder, and for that we need to build our decoder block first. Okay, let's begin with the decoder block. The decoder block takes 2 input. First is the input from the previous layer, that is here the input would be B1, and second it takes the skip connection, and here the skip connection would be S4. So you can already see the skip connection are passed through this res path, that is length time. Now first of all, it's going to, in the decoder block, it is first followed by a transpose convolution to increase the spatial dimension, that is height and width. So this transpose convolution doubles the height and width of this X feature map. Then it is followed by simple concatenation. Done. It's a simple. So that's what one change here is. We don't simply concatenate skip connection directly from encoder to decoder. We pass it through rest path to a number of time. Okay. Then finally it is followed by a multi-res block. Okay. And we return X, that is the output for this decoder block. What we're gonna do? We're gonna put 4 decoder block again. If you remember the diagram, we're gonna say decoder block input would be B1, skip connection will be S4, and then we're gonna say 256. So now if you wanna ask question why this S4, so let's solve this question also, because while concatenation we need the same height and width. Just remember that same height and width. So if you remember, the shape of B1 is 16 by 16. So let's assume B1 is 16 by 16. So here it comes to here. This X is 16 by 16 and it acts as the input to this. So from this 16 by 16, that is this X, that's the marks from here. Let's say 16. Okay. Now it passes through this and it became 32. Okay. From 16, it became 32. Now we need the skip. Now the skip connection would be of size 32 by 32. So let's print the shape of skip. We can say X dot shape. Let's check the shape of X also and shape of skip. Okay. So you're gonna see what are their length. That is the dimension. So you can see that dimension are 32 by 32 by 256, and again 32 by 32 by 250. So that's why we can concatenate them. But if you say as third here, let's say you say as third here, which is this skip connection, so they won't work because they don't have the same height and width. You get an error. You can see you get an error here. See line number 447. If you see line number 47, it's the concatenation. We can simply see why it doesn't work, because they don't have same height and width. So if you also see the layer, a concatenate layer require input with matching shape for the concat axis. Okay, so this won't work with S third. Its skip connection will be S4. Okay, so now I think things are more clear about the concatenation and rest of the thing. So what we're gonna do, we're gonna copy this and paste it here. So we're gonna say second decoder block input would be output of first decoder block, that is D1, and skip connection S third. Now we're gonna reduce the number of features to 128. Again we're gonna copy paste. We're gonna say D third input would be D2, skip connection S2, and number of feature again reduced by half, that is 64. Now D4 input would be D third, skip connection S1, and number of filters, that is 32. So now we again build the decoder block. So now comes the output layer. So first of all, before that, let's print the shape of the D4 and see if it works, because shapes are really important, because in a segmentation network the shape of the input and shape of the output are always the same. So here D4 should have exactly same shape as the input, and shape of the input is 256 by 256. So we want same shape, that the shape of D4 should be 256 by 256 and number of filters should be 32. Okay, now let's run it. Let's come back to the console and run it and see. Okay, so you can see it has the shape 256 by 256 by 51. Okay, 51 because of concatenation. And that, and now we can remove these two because they are also printing. Now we need an output layer which takes the D4 as the input. Okay, output layer is, so we need one as the number of output channel, one as the kernel size, padding is same, activation is sigmoid, because let's say we assume we are working on a binary segmentation problem. So now we're going to build the model, because we now has the input and the output for this entire structure. So we're going to take this model function, it take the input, output, and name of the network, and we're going to return the model. So we have implemented this. Okay, now we're going to print the summary of this model. We're going to say model dot summary. Okay, spelling mistake. Okay, now we're going to run it and see the entire structure. Okay, so you can see these are the total number of parameter. This is the output layer. Okay, that is 256 by 256 by So I'm going to reverse back to the entire network. If you see, let's go back to the top of this network and try to see the input shape first. Okay, so you can see the name of the network is MultiResUNET, as we put it here in this model function. The input layer is of shape 26 by 26 by 3 because of the number of channel, that is RGB. If you use a grayscale image with one channel, it would definitely work with that. It won't have any issue. Okay, let's again go back, and here we can see we have 1 as the input channel. See, 256 by 256 by 1, and there are the all the layer of the that is encoder, then we have the bridge, then we have the decoder. Okay, so this is all about the implementation of the UNET, not the UNET, that is MultiResUNET. So I hope I was able to give you some new information about the MultiResUNET architecture for this video, and if I did, then please make sure that you like, share and subscribe. And if you still have any question, then you can mail me or follow me on my social media, and all the related links for the code and rest of the thing are in the description. So thank you, have a nice day.